Good morning, everybody. It's a pleasure to welcome Jukka Vayrynen, who's visiting us today, and will give a seminar. So Jukka did his PhD at Yale and was at Microsoft subsequently before joining Purdue as an assistant professor. And he's gonna his work is in mesoscopic physics and quantum phenomena in nanostructures, and he's going to tell us about superconducting diode effects today.
Yeah, thanks, Michael. Can everyone hear me also on the Zoom? Maybe you can write in the chat if you can, they can hear me or not.
Yes.
Okay, great. Thanks, Michael, for giving me this opportunity to give the Fleet seminar here. And I'm a theorist, but today I will mostly discuss experimental work that was done in the group of Leonid Rockinson at Purdue. And that concerns this, what I call extrinsic superconducting diode effect. And then if I have time, I'll also discuss some theory work on this intrinsic superconducting diode effect. And I'll start by introducing what I mean by the superconducting diode effect and what I mean by intrinsic and extrinsic diode effects. Then in the first part of the talk, I will describe the Purdue experiment and our theoretical model for understanding it. And then if I have time in the second part of the talk, I will describe our theoretical paper that introduces the minimal ingredients to get an intrinsic diode effect in a quasi-one-dimensional superconductor. So the way I define the superconducting diode effect is as follows. So if you take a superconductor and you apply a current bias, and then you measure the voltage drop across the superconductor, you usually at small currents just get 0 voltage drop because supercurrent is dissipationless until once you ramp up the current beyond so-called critical current, a finite voltage will develop, and the superconductor switches to normal state. Now you can do the same experiment in the opposite direction. So you can reverse this bias current and then again measure the current versus voltage and find what is the critical current in this opposite direction. And the superconducting diode effect is the case when these two critical currents are unequal. Let me also mention that typically the critical current is a stochastic quantity. So in a real experiment, you often get a slightly different critical current each time. So what you need to do is a distribution of these critical currents. And in this talk, I will mostly just focus on the average value of the critical current, and I call that the critical current. And I'm not so much concerned of the shape of this distribution, just the fact that as long as these averages differ by more than the width of the distribution, we can have a well-defined notion of the diode effect. Now you can convince yourself that in order to have this diode effect, you need to break both time reversal and inversion symmetries, because under both symmetries, these currents switch directions. So to have the critical currents in the two direction unequal, you need to break both symmetries. And time reversal, we usually can break by applying a magnetic field. Inversion symmetry, you can break in two ways, broadly speaking, as I will explain. Now, this subject really picked up after this Nature paper by Ando et al., where they measured the critical current of this kind of layered superconductor formed out of niobium, tantalum, and vanadium when they apply in-plane magnetic field perpendicular to the current direction. So here I'm plotting the critical current as a function of this magnetic field, and at zero magnetic field, the critical currents are equal, but as you go to finite magnetic field, you get unequal critical currents, so you have the diode effect. And I would say that the precise mechanism is still unknown, but most of the theoretical works have focused on spin orbit coupling as the inversion symmetry breaking ingredient, and Zeeman interaction as the time reversal breaking ingredient. And there are lots of theory papers written about this. I won't try to list all of them, but I want to point out this very comprehensive and recent review just from last week from our fleet colleagues. So for a review of the vast literature of experiments and theory, you can look at this. Let me point out something interesting about this theory. Namely, there was an earlier paper from 1996 by Edelstein, where he studied spin orbit coupling and Zeeman interaction influencing the critical current of a superconductor. And he actually predicted that there would be a diode effect. However, this claim was disputed somewhat later in 2012. For example, in this book, there's a chapter by Achterberg where he claims that the critical current actually does not show any unusual asymmetry, differing from the conclusion of the paper by Edelstein. So there is still some debate, even on the level of theory, on this what I would call intrinsic diode effect, where intrinsic means that the inversion symmetry breaking comes from some kind of spin orbit coupling, for example. And I'm not the only one of this opinion. For example, in this recent paper, it was stated that while much ink has been spilled on the diode effect, the precise mechanism still remains unclear. Now, even more interestingly, so let me point out that spin orbit coupling, which occurs in heavy elements, might be something that comes to mind when you look at this layered superconductor. But actually, already in 2018, there was a very similar experiment with a layer of two superconductors, niobium and aluminum, and they actually saw the diode effect when they applied in-plane magnetic field perpendicular to the current direction. And in these materials, we don't expect strong spin orbit coupling. And in this paper, the interpretation of the result was attributed to some kind of geometric effect, which I will next discuss. So this is what I call an extrinsic superconducting diode effect. And in a two-terminal measurement, in my view, the simplest example is an asymmetric superconducting ring with a flux through it. So what the flux will do here is it will create a screening current or a diamagnetic current which circles the ring. And now if you apply external bias current, it's easy to see that the critical current that you would measure will be influenced by this screening current. For instance, you can see it this way. Suppose you look at the top half of the ring, and let's imagine that somehow you would be able to measure the critical current of the top half alone. And if you plot that critical current as a function of flux, you see that for positive flux, the critical current goes down because you have extra screening current that you need to be able to support. Whereas for negative flux, the screening current changes sign. So now you can actually put more current through the top half. So the critical current would increase. And let me just clarify here that I'm looking at small fluxes much below the flux quantum. This whole picture will actually become periodic in the flux quantum, as we will see soon. Now, if you do the same thought experiment for the bottom half, and I'm drawing the bottom half as thinner, meaning that it has smaller critical current, then you will actually get a line with the opposite slope, because the screening current contributes with opposite sign to the bottom half. And also the intercept at zero flux is smaller because the critical current of the bottom half is smaller. And then I claim that the total critical current of this device is actually given by the minimum of these two critical currents. And if you reverse the bias current, you would get something like this. And by taking the absolute value, you see that you would expect the diode effect as long as you are at non-zero flux. And this is actually what people see experimentally. So the picture seems to work. So for example, here, this is from Leonid Rockinson at Purdue. They have a superconducting ring, and the critical currents exhibit the diode effect, and it's periodic in the flux quantum. Also, let me mention that there are other ways to get extrinsic diode effect. Perhaps the simplest one is to use a three-terminal system which is in this paper, but I won't discuss that any further. So let me describe the experiment at Purdue. They had this heterostructure of aluminum and indium arsenide. So indium arsenide is a semiconductor with strong spin orbit coupling, and it will be proximatized by the aluminum on top of it. So you basically will get a layer of two superconductors, aluminum on top and the proximatized indium arsenide on the bottom. And then what experimentalists do is they etch out aluminum from certain regions to make these wires, narrow wires between two banks of aluminum, and they apply a top gate to deplete the indium arsenide from the green region. However, the indium arsenide, which is under the aluminum, will not be depleted because aluminum screens the electric field or the voltage that you apply. So basically you get a shadow of the aluminum in the indium arsenide layer, and that shadow will be populated with electrons and becomes superconducting. And in this setup, they measured the critical currents, and they saw that when you apply magnetic field perpendicular to the current direction and in plane of the layer, they saw the diode effect. And here is the kind of full data. And as you can see, it's a bit more complex than in the Landau et al. Experiment. And we can quantify this by plotting the difference of the two critical currents. And what you see is that there seems to be almost like a periodic structure, although you barely see more than one period. But still, it looks like there's a period of maybe 400 millitesla in this kind of size of the diode effect. Also, it seems like you get a sign change in the diode current, and this was seen in multiple samples with different wire lengths, and that's important because the first thing we thought about was that there would be a flux that's threaded through this area formed by the wire and the barrier, but in fact this period is not related to that. It seems to be independent of the length of the wire. So these three curves are different lengths, and these arrows point the expected period from this area. So the actual area, which gives the observed 400 millitesla period, is actually much smaller. Also, you see that the temperature or application of a parallel magnetic field does not seem to change the periodicity, although the parallel field does suppress the magnitude of the diode effect. So these were the mysteries that we wanted to explain with theory. And the theoretical model that can at least qualitatively explain the observations is a fairly simple one. We call it the two-wire model. Basically, you take two one-dimensional superconductors to model the aluminum and indium arsenide wires. And you can write the supercurrent for each wire with magnetic field going out of the plane through the wires or in between the wires. And the key ingredient is that the supercurrent has this prefactor, which is the kinetic inductance of the wire that depends on superfluid density. And this superfluid density is very different in aluminum and indium arsenide, which makes these kinetic inductances also different. And we can solve for the phases in each wire by requiring current conservation, and second, assuming strong Josephson effect, which actually locks these phases to be equal. And once you lock the phases equal, you only have one unknown phase, and you can solve this this current distribution. And in fact, you find that there will be a diode effect as long as the two kinetic inductances are unequal, and this diode effect increases with the magnetic field linearly, and it basically arises from the diamagnetic current that you induce in each wire. So this explains the first increase or development of the diode effect, but this predicts that the diode effect should keep on going, increasing linearly with the field, which experimentally was not seen, of course. And the reason we think the diode effect eventually becomes smaller is because at high magnetic fields, the screening currents will start to cost kinetic energy, and it becomes actually preferable to form a Josephson vortex. So you break the phase locking condition to save some kinetic energy. And basically, the system wants to form these Josephson vortices at high magnetic fields, and the size of the Josephson vortex is given by this Josephson length. This Josephson length, which is some parameter that only depends on the kinetic inductances and the Josephson energy. So it doesn't depend on the length of the wire. Okay. And next, you can do energetics to figure out when, at which magnetic field you should start creating the Josephson vortex. And basically you can derive something like energy landscape that looks like this. And this gives you the field values where it becomes favorable to go to a phase distribution that has, let's say, one Josephson vortex as opposed to having 0. Also, if you have quantum fluctuations, we expect that you smear out these cusps in the ground state energy. And this is very similar to persistent currents in superconducting rings that was studied in the early 2000s, where it was seen that quantum fluctuations actually smear out the current phase relation from this sawtooth shape to something that becomes sinusoidal. And it's the same thing that basically happens in our case. So you can show that the delta I, the size of the diode effect, would have a sawtooth shape if you didn't have quantum fluctuations, and it becomes sinusoidal when you do have quantum fluctuations. Now, we need to include one more ingredient in the model, which is the suppression of the amplitude of these oscillations. And we believe this is because the magnetic field suppresses proximity effect. So it's known that indium arsenide actually becomes unproximitized at a certain magnetic field of order 700 millitesla, which is applied in plane. And we include this effect completely phenomenologically by taking the superfluid density of indium arsenide and just multiply it by a suppression factor, which is linear in the in-plane field. And this actually will make the sawtooth into this kind of function. And if you include quantum fluctuations, then this function becomes more like sinusoidal, and its amplitude goes down because you lose the proximity effect. And a shape like this is perhaps what was seen experimentally. This also explains how you can include the in-plane field along the wire, which is seen to just suppress the amplitude, but not change the period of the diode effect. And this is more or less in agreement with the corresponding experimental observation. So in summary, we think that the effect eventually goes away because we lose proximity effect in indium arsenide. Also, the period we think is explained by size of the Josephson vortex. The unfortunate thing is that we cannot calculate theoretically the Josephson vortex size because we don't know the Josephson coupling strength in this layer. We, however, do know the electron densities in aluminum and indium arsenide, and from those you can get even quantitative agreement with the slope of the diode effect near zero field, where there is no Josephson vortex created yet. So that at least gives us some quantitative agreement with the experiment. So the key conclusion to make from this is that whenever you have two coupled dissimilar superconductors, you will quite generically have a superconducting diode effect. And with this kind of model, we were able to explain the observed phenomena in this aluminum indium arsenide wires. Also, it's unlikely that this would be intrinsic effect because the experimenters saw no dependence on the orientation of the wire relative to the crystal axis. Whereas, at least from simple spin orbit consideration, you would expect there to be a difference in the size of the diode effect, depending on which crystal axis the wire is along. Okay, so that was the experimental part, and I will now, in the remaining time, discuss our completely unrelated theory work, which outlines the kind of minimal ingredients to get an intrinsic diode effect in quasi-1D superconductors. And this theoretical work is based on a low energy model, which basically is justified because in the case when the critical current is determined by Cooper pair depairing, which is basically a Fermi level property or physics. So it should be okay to use a linearized low energy model. And the linearized model has two modes near the Fermi points in the normal state. And moreover, we will divide the system into helical bands. What I call by a helical band is a band where the right mover has, let's say, spin up, and the left mover has the opposite spin down. So, for example, a conventional spin degenerate S-wave superconductor would have two helical bands which are identical because of the spin degeneracy. And the single helical band, on the other hand, would be relevant to something like the edge of a 2D topological insulator. So even though this is not the usual case, it's illustrative to start with this single helical band. And when we add S-wave pairing between KF and minus KF, what we usually do is we draw the hole bands, which are in the dashed lines, and then we open gaps between the electron and hole bands. And you can find the spectrum of the system that has now superconducting gap. Next, we apply supercurrent, which we do by including a Cooper pair momentum in the order parameter. So basically a phase that has a constant gradient. And this Cooper pair momentum Q can be related to the supercurrent in this simple way. And what I will find is actually what we call critical Cooper pair momentum, and that will then uniquely determine the actual critical current. So I kind of treat those two quantities as synonymous in the rest. So basically what happens when you apply this supercurrent, you get this linear term in the dispersion, and what it does is it moves these bands up and down, and the critical current is reached when one of these bands crosses the Fermi level, which happens in this case at Q equals delta over V. So once you have this critical momentum, you can now generate quasi-particles without any energy cost. So the system becomes is no longer dissipationless. And if you reverse the current direction, you just get the opposite value, but with equal magnitude. So in this case, there's no diode effect until you apply Zeeman field. Namely, interestingly, in this one helical band case, the Zeeman field enters actually the same way as the supercurrent, and it leads you to this kind of phase diagram with the critical current on the y-axis and Zeeman field on the x-axis, and you see that there is in fact a diode effect whenever the Zeeman field is non-zero. So basically, if you sit at current bias magnitude, let's say here, then by reversing the current, you will enter the normal state in the opposite direction. Now, so this was for a single helical band, which is maybe somewhat difficult to measure even in a 2D topological insulator, because any two-terminal measurement actually has two edges that it would couple to. So when you add the other helical band with opposite helicity, then in fact you will get another phase diagram like this, but with opposite slope for the Zeeman field. So in total, you get this kind of phase diagram, which is fully reciprocal. So you don't see a diode effect in this case. However, just phenomenologically, you can see that if you don't consider identical helical bands, but rather helical bands that, for instance, have different Fermi velocities, then you immediately create this kind of asymmetry, which gives you the diode effect. You could use other ingredients as well, for example, different induced gaps or different G factors, but we thought that this case of unequal velocities is actually the simplest. And where you could find such unequal velocities with two helical bands, actually you can go to a Rashba system with some extra ingredients. You might know that the regular Rashba system actually has equal Fermi velocities, but there are at least two ways to make them unequal. The simplest one is maybe on the bottom. If you apply a magnetic field along the wire, then you open a Zeeman gap here, and this is the topological gap, in fact. And what it gives you, at least at chemical potential close to this bottom of the band, these orange velocities become smaller than the blue ones, and you should have the diode effect. Now, even without this magnetic field, if you have a quasi-1D system that has multiple subbands, you can have a scenario where one of the transverse subbands basically pushes the lowest subband, the inner modes in the lowest subband, in such a way that these will, the inner mode obtains a smaller velocity. So this is perhaps the simplest way, because it doesn't require Zeeman field, and it should happen in any finite width wire. And indeed, with this, we can estimate the size of the diode effect. It turns out to be a small effect. And in our paper, we also find the dependence on the width of the wire. So let me just give the conclusions here, and then I'll wrap up. So basically, whenever you have two helical bands with unequal Fermi velocities, you should get the superconducting diode effect, at least when the critical current is determined by Cooper pair depairing. But this diode effect is generally quite small. It's always proportional to the ratio of the velocity difference to the average velocity, which typically is a small quantity. And for more details, you can look at this paper. So let me wrap up here. And here are my co-authors, and I'm happy to take questions, and thank you.
Are there any questions about the either online, or you guys have any questions? Yeah. So this, I mean, in the first part of the work, you showed that if you have two different superconductors, then you generically get this extrinsic effect. But this, I guess, does not explain these multi-layers with tantalum, vanadium, niobium, or do you think it's part of the story?
I think it might be part of the story.
Okay.
Sorry, the mic wasn't on. Yeah, I think it might be part of the story, but the key question is how to differentiate between the two mechanisms, the intrinsic and extrinsic ones. I think what you need to do always is to measure along different crystal orientations. But even then, it may not be clear what the intrinsic effect will give you, or it may be theoretically hard to predict, because we don't know these exact spin orbit strengths of different types of spin orbit couplings and so on. So it may be theoretically kind of hard to predict what you would expect in different crystal orientations. So even if you have, even if it came from spin orbit, you might have some kind of contrived spin orbit couplings so that the result is independent of the orientation, and then it would look exactly the same as the extrinsic effect.
You guys have questions?
Not at the moment.
Okay.
All right. Well, let's thank Jukka again for a nice talk.
Thanks.